All right, so in our next section, we're going to be taking a look at dividing polynomials. This is section 5.4. We're going to be looking both at synthetic and polynomial long division. So since I'm actually recording this on a Thursday, we're going to have a little throwback Thursday here. And we're going to go back to division when you first learned it with real numbers. Okay, so let's divide 2,172 by 3. And we're going to do it the old way. All right, so we're going to have 2,172. I'm going to divide it by 3. So if you remember this process, we start and we look, does 3 divide 2? In this case, it doesn't. So now we ask, does 3 divide 21? It does, and it does so 7 times. Now, I put that 7 directly above the term where I just divided. Then I multiply 7 times 3, and I write that result 21 underneath. I'm going to subtract this entire line. In this case, I get a 0, right? And now I bring down my next term, which is 7. Okay, so now I say, does 3 divide 7? It does, and it does so twice. 3 times 2 is 6, and I write that below. I'm subtracting this whole line, and I get a 1. And now I bring down my next term, which is the 2. So now I have 12. 3 divides 12 4 times, and I write that above. 4 times 3 is 12, and I subtract, and I get a 0. So the old way of dividing, all right, with long division, right, what I just did is I took 2172, I divided it by 3, and I get a result of 724, okay? One other thing that I could do is I could actually write this, if I multiplied both sides by 3, now that we know some algebra rules, as 3 times 724, right? Because I ended up getting a remainder here that was 0. Okay, that's a really key part of my ability to do this, okay, or at least to write it that way. So, pardon me, a couple of properties here. If I have two functions, g and f, right? If g is a factor of f, then f is divisible by g. So think about it in terms of real numbers, right? So 1, 2, 3, 6, 9, and 18 are all factors of 18, and also 18 is divisible by 1, 2, 3, 6, 9, and 18. Okay, just that same property that works for real numbers is going to work for division. Similarly, x to the 4th minus 81 is going to be divisible by x squared plus 9, x squared minus 9, x plus 3, and x minus 3, because those are all factors of x to the 4th minus 81. Those are all of the factors. Because x squared plus 3x plus 1 is not a factor of x to the 4th minus 81, it will not be divisible by x squared plus 3x plus 1. So we're going to use what's called polynomial long division to find a quotient and a remainder, and also to use to help us factor polynomials. So steps for dividing polynomials, right? I will print this slide off and give you guys a copy of it in class. So the first step, we want to make sure the polynomial is written in descending order, so in standard form. And if there are many missing terms, we're going to replace them with a 0. So in that last example, x to the 4th minus 81, we're going to have to write that as x to the 4th plus 0x cubed plus 0x squared plus 0x, and then minus 81. I need these placeholders for all those missing terms or it's going to screw us up. Okay, they have to be there. Okay, I'm going to divide the term with the highest power inside of the division symbol by the leading term of the term with the highest power outside of my division symbol. Okay, whatever I get as a result, I'm going to write above the term I just divided. Okay, I'm going to multiply that value that I just got, and I'm going to distribute times the polynomial in front of the division symbol. So I'm going to get a new polynomial, and I'm going to write it underneath. Okay. You're going to need to use parentheses because I'm going to subtract that entire line. So if we're subtracting the entire line, make sure you distribute that negative to each of those terms in that polynomial. Then we're going to repeat steps 1 or 2 through 4 until there are no terms left to bring down. Okay. When we're done, we're going to write the final answer, whether it's in quotient and remainder form or whether it divided out with no remainder. We'll look at what that looks like in different forms. Okay, so let's try a couple of things here. You will notice as you scroll through the notes, there are a few, I believe it were 3 examples of long division that were already typed out that I typed out a couple years ago. I took them out of the video just to save time, but they are there for you guys to take a look at. Okay, I'm going to go through the process here in a second a couple of times. So if a polynomial f of x, this is a remainder theorem, if a polynomial f of x is divided by x minus c, then the remainder is f of c. So think about this. If I took this divisor x minus c and it's linear divisor, and I solve it, right, this is going to give me x equals c. And thus, my remainder of the factor, when I divide long division, x minus c, the remainder is going to be f evaluated at c. Okay, so here I've got polynomial f of x equals 3x minus 3x, or sorry, x cubed minus 3x squared plus 5 plus x. We're going to divide. I want to find the remainder of f of negative 2, or I want to use the remainder theorem to evaluate f of negative 2. Remember that f of negative 2 would have come from a factor of x plus 2. So I'm going to divide by x plus 2. So again, I want to take my lead term inside divided by my lead term outside. So x cubed divided by x is going to give me x squared. Right? You don't have to write that off on the side. You can just do that. All right? So I'm going to write an x squared right here above the squared term. Now I'm going to distribute. X squared times x gives me x cubed. X squared times 2 gives me 2x. And I want to subtract this entire line. All right, so when I subtract this entire line, x cubed minus x cubed is 0x cubed, which is what I want. Negative 3x squared minus 2x squared is going to give me negative 5x squared. All right, I bring down my next term, which is positive x. So now I divide my lead term here, my new lead term. So negative 5x squared divided by x, and I'm going to get negative 5x. All right, negative 5x times x gives me negative 5x squared. Negative 5x times 2 gives me negative 10x. And again, I subtract this entire row. All right, negative 5x squared plus 5x squared is 0, all right, which is what I want. I always want that lead term to cancel. X plus 10x gives me 11x. And now I bring down my next term, which is positive 5. All right, 11x divided by x gives me 11. And I distribute. 11 times x gives me 11x. 11 times 2 gives me 22. And I subtract this entire line. Okay? 11x minus 11x is 0. And 5 minus 22 gives me negative 17. Okay? So what this tells me then, right? This is my remainder, this very last piece here, just like it is in regular long division. So what it then tells me, okay, is that f of negative 2 equals negative 17. Okay, if you were to plug negative 2 into this polynomial, you are in fact going to get negative 17 as a result. Now, you might be saying, why in the world would I ever do this? You're probably not going to for the purpose of evaluating a function. Although when we look at synthetic division, if you have something really messy and you don't have a calculator, synthetic division is arguably easier, all right, than actually evaluating it at times, okay? But in terms of long division, to evaluate a function, we're probably not necessarily going to use it. But what the remainder theorem does lead us into is another theorem that we're going to talk about later, which is really, really helpful, okay? In the meantime, I also have the intermediate value theorem, okay? So let me do this in a slightly brighter color so it's easier to see, okay? So I have some polynomial function here, right? And at our point f of a, I have a value that's negative. At my point f of b, I have a value that's positive. That means that at some point, at least once between those two terms, between x equals a and x equals b, there must be some value in the middle here where we have the polynomial equal to 0, or I have an x-intercept. Okay, so what the intermediate value theorem says is, we have a polynomial. If f of a and f of b have opposite signs, then there exists at least one value between a and b such that f of c equals 0. Okay, now here's the thing. We could have multiple places where we cross. Like we could have something that between those 2 points, okay, maybe my graph comes up and does something like this, and maybe I have multiple zeros there. It doesn't tell me how many exist. It just tells me that at least one must exist. If I go from negative to positive, I had to cross 0 at some point. Okay, and this works for any continuous function, and all polynomial functions are, in fact, continuous. Okay, now I said there was another theorem we were going to talk about, that the remainder theorem, where that's really useful, and it is the factor theorem. So a polynomial f of x has a factor of x minus c if and only if f of c equals 0. So if I essentially evaluate the remainder theorem and I get f of c equals 0, I get a remainder of 0, it then tells me that either x equals c is a 0 of the function, or that x minus c was a factor of the function. And in fact, x minus c times the quotient, right, that I have on top of my division symbol is a factored form of my original polynomial. Okay, so I want to show that x minus 2 is a factor of the function x cubed minus 4x squared plus 3x plus 2. So I'm going to divide x minus 2. I'm going to divide x cubed minus 4x squared plus 3x and plus 2. Okay. So again, I'm going to start with lead terms here, right? So x cubed divided by x is going to give me x squared. I multiply x squared times x gives me x cubed. X squared times negative 2 gives me negative 2x squared. Again, I'm subtracting this entire line. X cubed minus x cubed is 0. Negative 4x squared plus 2x squared is negative 2x squared. I'm going to bring down my next term now, right, which is a 3x. Okay, I'm going to divide the lead term, right? Negative 2x squared divided by x. Negative 2x squared divided by x is negative 2x. I distribute, I get negative 2x squared plus 4x, and I'm subtracting this entire line. Here I'm going to get a negative x. Then I'm going to bring down my next term, which is a 2. I'm dividing the lead terms. X divided by negative x is negative 1, right? Excuse me. Negative 1 times x is negative x. Negative 1 times negative 2 is 2. And I subtract this entire line, and I get a remainder of 0. All right, so what I get in two different forms of writing this is that x cubed minus 4x squared plus 3x plus 2 divided by the x minus 2 equaled x squared minus 2x minus 1. Or again, if I do that same thing where I multiply both sides by my denominator here, I find that x cubed minus 4x squared plus 3x plus 2 equals x minus 2 times x squared minus 2x minus 1. So what I get is a factored form of my polynomial, specifically because I had a remainder of 0 here. Okay. So finding a polynomial with known zeros, right? So if I have a polynomial with zeros of 3, negative 1, and 1, right? I want something degree 3. I have 3 zeros here. I'm good, all right? I want to work backwards, find that polynomial, right? So I want to work backwards here. X minus 3 equals 0 was the factor that the x equals 3 had come from. And thus I also get x plus 1 and x minus 1 equal to 0 as well. So I have some polynomial f of x equals x minus 3 times x plus 1 times x minus 1. Now, if I just word it this way, find a polynomial of degree 3 with the following zeros, you're done. If, however, I said find it in standard form, then we need to multiply it out. But here, for this purpose, we're finished. We have the polynomial. what we're going to start doing here in the next couple of days is now going from the ability here to go from zeros to the function. I want to go from any function in standard form, assuming it's a function that factors, and find all of those zeros. Okay, that's our end state. That's where we're going here in the next couple of days. There are a couple of extra examples, so if you want to look at a few more, click on this link. It's going to show you a few more worked out examples with some explanations and notes in terms of polynomial long division. All right, so the next thing we're taking a look at is synthetic division. Synthetic division is another form that we can use, or another method we can use to divide polynomials. It is a little bit more efficient. It is a little bit quicker. However, it's only going to work in certain cases. Polynomial long division works every single time, regardless of what type of functions I have. Synthetic division only works with linear factors. Okay, so I must have linear factors. I must be able to write it as a single x equals c. Okay, the two examples that I worked out for long division here a little bit ago, both happen to be linear divisors, right? But two of the ones that I worked out prior to that were quadratic divisors that we worked through. So in synthetic division, you're going to write everything in terms of just coefficients. So here I'm dividing, in this case, I'm dividing x equals 2. Or dividing by x equals 2. And here, each of these terms inside represent a term, okay? So here I have 3x cubed plus 4x squared minus 3x plus 2. We're just going to write them without any of the actual values. So here's the process. So I take that first term and I bring it down below. I just drop it down and it's there. Now I'm going to multiply my divisor times that new value at the bottom. So 2 times 3 here gives me 6, and I write it up at the next line. Now I add these two values. When I add these two values, I get the 10, and I write it down below. Now I take the 2 times the 10 and write it up above, and I get a 20. Now I add, negative 3 plus 20 gives me the 17. I repeat, 2 times 17 is going to give me a 34. 2 plus 34 is going to give me a 36. So for this particular function up here above, if you think about it in terms of the remainder theorem, right? So f of 2 is then going to equal, in this case, 36. Okay? So it doesn't divide. It's not a factor, all right? We have a remainder, but I could use that to evaluate the function here in the event that I didn't have a calculator or I didn't want to do some really messy math, okay? So synthetic versus long division for the same two problems here. Here's a comparison of the work. Anytime I have the option, I always go to synthetic division. It's faster, it's easier, it's less work, it's less chances to make a mistake. Again, you need to know long division because you're going to have places and times where synthetic division will not be an option for us. So I'm going to try a couple here. So I have the polynomial f of x equals 4x to the fourth minus x cubed minus 3x squared plus 5, and I'm dividing it by x plus 3. Now remember, with long division, or with synthetic division rather, I'm not dividing by the factor. I need to write this and solve it, set equal to 0, so I get x equals negative 3. The other thing that you're going to notice here is I'm missing a term. And just like with long division, I need to replace that term with a 0x to the whatever power placeholder. So here what I'm going to do is I'm going to start with my polynomial function. So we're going to have 4, negative 1, negative 3, 0, and 5. Okay? And I'm dividing this by negative 3. So let's go through the process. So I bring down the 4. I multiply negative 3 times 4 gives me negative 12. And I add negative 1 plus negative 12 gives me negative 13. 3 times negative 13 is 39. Negative 3 times 39 is going to give me 36. All right, 36 times 3 is going to give me 108, negative 108. And 3 times negative 108 is going to give me positive 324. Now, I typically put a vertical bar here before the last term, and I'll talk about why here in a second. And here I get 329. So this portion to the left of that bar before the last term in the bottom row, this is my quotient. This is my remainder. Okay, so here I found that f of negative 3 in this case is going to equal 329. All right, so let's do a little bit more with synthetic division. So I want to show that negative 11, right, so x equals negative 11 is a 0 of the polynomial, which is going to also imply then that x plus 11 is a factor. Okay, so I have this polynomial x cubed plus 8x squared minus 29x plus 44, right? So here we're going to divide negative 11, or by negative 11, we're going to divide 1, 8, negative 29, and 44. Again, I'm going to repeat the same process, right? I'm going to bring that lead term down, so I'm dropping down the 1. Negative 11 times 1 is negative 11. 8 plus negative 11 is negative 3. Negative 11 times negative 3 is 33. And negative 29 plus 33 is 4. Negative 11 times 4 is negative 44. And I add that last column and I do get a remainder of 0. So again, what I got here, remember I said this is my quotient, right? So just like before where I'm looking at this in terms of only the coefficients and none of the variables, these are in order. So this has to be the squared term, the linear term, and the constant term, right? Times my factor of x, in this case, plus 11, okay? And if I wanted to continue factoring this, right, I could continue on from here. Think about it. I know here I had x plus 11. And here, x minus 4 times x plus 1. And actually, no, that's not going to work. Never mind. Okay, so that one's not going to factor nicely. It's going to need the quadratic formula. So I was going to show that if this factored nicely, what I could do is stack another division here by some number, and I could divide through, and I would get, in this case, a linear term. But that's not going to work out very nice. I need something that's going to come from the quadratic formula in this case. Okay. So, one last example, f of 3 I want to evaluate using the remainder theorem. So I'm going to divide by 3, right? Dividing this polynomial, all terms are there. So I get negative 3, 1, negative 3, negative 1, and 15. So again, we're going to divide here. I'm going to drop down that first term, so negative 3. Negative 3 times 3 is negative 9. I add, I get negative 8. 3 times negative 8 is going to give me a negative 24. I add, I'm going to get a negative 27. All right. 27 times 3 is going to give me negative 81. And I add, I get negative 82. Again, bar at the last value for my remainder. Negative 82 times 3 is going to give me negative 246. 15 plus negative 246 can give me negative 231. So here, from the remainder theorem, we find that f of 3 is negative 231. And I would argue that that was a lot easier to do than actually working through it and substituting in and trying to evaluate this, right? You're going to have some big numbers, and I could probably do it quicker here with synthetic division. So the end state here, and a quick little checkpoint, and we had a checkpoint the other day, but you should now be able to recognize that the following things are true. So if I have f of a equals b, then the following are true. AB is a point on the graph of f. the value of f at x equals a equals b. Thus, f of a equals b. It's just by definition of function notation. If f of x is divided by x minus a, then the remainder is b. Okay. Furthermore, if b equals 0, then the following are also true and also interchangeable. Okay. The number a is a 0 of the function f. The point a0 is on the graph of f, and a is an x-intercept. The number a is a solution to the equation f of x equals 0, and the binomial x minus a is a factor of the polynomial f of x. Okay. The next thing that we're going to take a look at is zeros of polynomial functions, and then we're going to really start tying together a couple things we talked about the other day, all the division stuff, and we're going to start looking at how to factor and solve any polynomial of higher degree. All right, have a good night. We'll see you guys tomorrow.